So now log in into the Edge Impulse or sign up for a free account. Then create a new project. Give it a name. And create. Okay, so for the devices section, now Edge Impulse provides specific data capture firmware for many boards on the market. At the moment, the Arduino RP2040 Connect, the one that we are using here, is not, to my knowledge, fully supported for real-time streaming. If this is your case, you probably have at least two other options. The first one will be to forward your data using a data forwarder service via perhaps MQTT broker like Mosquito, where supported IoT platforms can stream data in real time. However, in this work, we have opted out for the easiest solution where data will be uploaded manually. So let's upload our data. Click on Add Data, Upload Data. Now before choosing your file, you could go to the Configure wizard. It's very easy to look at your data to see if they are compatible or if there are any processing required. So choose your file. Normal data or any file you wish. That looks okay. Next. Yes, it's the time series. Each row contains a reading. Timestamp is the time column, milliseconds. Okay. We'll keep it as one file. Now choose your files. We're going to choose the 3 files all together. Scroll down, upload, and if you get any errors, it should show up here. Okay, so now we have the 3 folders here. So the first file is our testing data. So we're going to move this to the testing set. We're going to add some useful labels. So we're going to call this as a normal engine, normal running engine. And this is a normal If you go to the testing file, this is the testing for normal running engine. Now our data is ready. We will design our impulse. So for our data, based on the cycling nature, I will be choosing 5050 millisecond. And with an increase of around 500 milliseconds. Before creating our learning block or k-means, it is essential to perform spectral analysis on the data. This will allow us to understand the underlying structure, characteristics, and so on. So we're going to click on Add a processing block. Due to the nature of our repeated signal, because of the accelerometer and gyroscope data measuring a continuous or cycling vibration, we will be looking at the spectral analysis block here. So we're going to add one. And for our k-means, we can add a k-means block. That's the anomaly detection k-means. We can also add a classifier here. Let's try that one as well. Put k-means as well. Alright. So if you click here on Save Impulse, then on the left hand side you will see that all the blocks that you have added shown on the left hand menu. So in the Spectra feature you can see that you have the engine on data, or from the drop down menu you can choose when the engine is off. This is your raw data. Each number here represents a measurement or observation. So filters in general can be applied to pre-process any sensor data before analysis. Now these filters can be low pass, high pass, band pass, notch filters. And applying filters can really help remove the noise and isolate specific frequency components, and this is what we are really after, because the engine during a running state you can see that it is oscillating in a certain pattern, and when it's in an idle resting state it's also having a certain specific frequency parameters to it. Setting the scale axis to 1 helps in ensuring a uniform scaling, maintaining the aspect ratio of plots for accurate interpretation of data. Whereas the input decimation ratio specifies how much original sample rate should be reduced before further analysis within the platform. So when we keep a ratio of the input decimation as 1, this means no decimation is applied. And this means that we are retaining all samples. Because of the nature of our oscillations somehow, so we can use a high filter here. This is the cutoff frequency. And the order of the filter specifies how sharp the cutoff slope is. Now the type of the analysis, we have two options here. We have the wavelet and we have the fast Fourier transform. Now the wavelet is actually more suitable for localized analysis of spectral features. It allows analyzing the signal or decomposes the signal into different frequency components at different scales. Whereas the fast Fourier transform is more of a fixed resolution. So the FFT decomposes the time domain signal into frequency components, but the resolution is determined by the length. So when we choose the number 16, this determines the resolution used, or the resolution of the FFT window. A higher number means more resolution and more computational resources. Shorter FFT provide lower frequency resolution but are faster to compute. So in general, if you have a non-transient signal oscillating, cycling over a period of time, FFT is more suitable. Whereas if you really have a transient state within the signal and you need to capture and analyze those, then wavelet will be your option. So we're going to keep the take log of spectrum ticked. Taking the logarithm of the spectrum can help compress the dynamic range of the data, making it easier to analyze and visualize, especially when dealing with large variations in signal magnitude. And we're going to keep the overlap FFT frames ticked. Overlapping the FFT frames involves shifting the analysis window by a certain amount. This can help improve your temporal resolution. So we're going to save the parameters, and on the top click on the generate features. If you get any errors, that should be shown here. Okay, so job completed. Now we're going to see the outcome of this DSP toolbox. Remember, you can always as well customize your DSP tool here. So if you're looking at a specific peak, if you're looking for the power spectrum of a specific peak, then you can design this and then use it here in Edge Impulse. I'm going to zoom out a little bit. Okay, so we have here clearly two distinct clusters. The orange one is when the engine is running, so all the data of the running engine is clustered in the right hand side here, and the blue ones are when the engine is off, and you can see they are two distinct. So now we have our data clearly clustered. We can go to the classifier. Now the classifier is not necessary in this work. You can still use the anomaly detection model without using a classifier. So looking at the training settings, the number of training cycles. This settings determines how many times the training data will be passed through the neural network during training. For a start, 30 training cycles seems okay. The Learned Optimizer is not free with the free account. Looking at the learning rate, now the learning rate controls the step size of the optimizer. So a smaller value or smaller learning rate means smaller steps and slower conversions. A value of 0.0005 is often a good starting point. So the CPU setting determines whether the training will be performed on the CPU or somewhere else. This is suitable normally for small data sets like the case we have here. Let's move on to the advanced training settings. The validation set size. So a validation set size of 20% means 20% of your data will be set aside for validation. So we're going to keep this as is. When it comes to the batch size, this determines the number of samples processed by the neural network in each training step. Normally a batch size of 32 is a common choice. The auto-weight classes, this option adjusts the loss function to account for class imbalances. Now the last setting, it profiles the model using the 8-bit quantization. This reduces the precision of the model's weight and activations to 8 bits. Now the benefit for this is that it can lead to a smaller model size and hence a faster response. This is essential for low-power microcontrollers and resource-constrained devices. These are the network architecture. We can start training. So any errors should show up in the output screen here on the right hand side. Model training complete, job completed. Well, there is not much in this step, and the fact that the model can recognize between when the engine is off and when the engine is running. The green ones are the one for the engine running, and the yellow one for when the engine is off. Alright, so let's keep going. Anomaly detection. So here I'm gonna choose 2 clusters, and I will be choosing the root mean squared values for all the values obtained from the accelerometer and the gyroscope. And let's start training. Any errors should show up in the top right output window. Okay, job completed. Just move the window a little bit. Okay, so you can pick whatever axis you wish to see the relation with the other one. So you can pick 2 gyroscope data, and you can see the cluster formation and so on. Now this is based on the training data, but if you would like to test this model using the testing data, you can click on the test data, and we hope that they are within the same cluster because they are a split of the original file, and this is what was the case. So the orange are the tested data and the blue are the training data. Now that's important, the anomaly score. Now this indicates the degree of deviation or abnormality of each data point from the expected normal behavior. Now the range of anomaly score is provided here. It says a minimum of a -5.0044 and a maximum of a -1.0157. Now the lower the anomaly score typically indicate the likely or the higher likelihood of the data being anomalous. Okay, so if we get a score of a -5, means it's a highly likely it is abnormal data, or it is deviating from the normal pattern. Now if we get a score of a -1, on the other hand, this is more closer to the normal behavior. And the final values shown here, the average axis distance, this shows the average magnitude of both acceleration and the gyroscope readings across different axes. Now we have the anomaly detection done. Edge Impulse provides you with the EON tuner. This is a feature that can assist in optimizing the machine learning models for deployment on low power microcontrollers and resource limited devices. Whereas you can in fact go to your model testing, depends what you are doing. You can do a live classification, which does not apply in our case. We're gonna just jump on in a minute for the deployment. One of the nice features the EON tuner has is that it's specifically designed to help balance the trade-offs between model accuracy from one side and the resource constraint on the other side. So this will allow a better memory usage and reducing any delays in the inferencing step. So we're going to go now to deployment. Click on the Arduino library. Okay, and simply click on build. Alright. You can see that under the build output, the job is completed. Now the build output is successful, we need to check the download folder. The Arduino library created by Edge Impulse is downloaded as a zip file. We need then to add this as a library in the Arduino IDE. We will go over the steps in a minute. As you can see here, the download is still in progress. This is the library is being downloaded, and this is the library created by the Edge Impulse. So all what you need to do now is to go to Sketch, Include Library, Add Zip Library, and navigate to the download folder, where you will find the zip file that was created by Edge Impulse a few minutes ago. Make sure you add this library and make sure you get a message here that the library was added. Then go to File, Examples. You can go to Static Buffer. This is the basic code provided by Edge Impulse to you. Now we have to do some modifications. So we have to make sure that the real-time data from the accelerometer and gyroscope are acquired into the features array. We will do some modifications on this code, and perhaps we may add a condition if anomaly is below or higher than a certain value to turn on an LED and so on.